Hello there. In this sections we get an overview on how to move hydrogen around to customers using it. Hydrogen is a promising energy carrier, but transporting and storing it efficiently presents challenges due to hydrogen's low density, high flammability, and need for special conditions. Different methods exist to transport hydrogen over short and long distances, each with advantages and limitations. Similarly, storing hydrogen requires safe and efficient technologies that depend on the specific application. Now we will look at key transportation methods and storage technologies and their practical applications. Hydrogen can be transported in gaseous, liquid, or chemical forms. The choice depends on distance, infrastructure, economic, and safety factors. One way to transport hydrogen is in gas form. There are two main technologies for this: pipelines and compressed hydrogen tanks. First, pipelines. Hydrogen can be moved through dedicated pipelines that are built only for hydrogen, or it can be blended with natural gas in existing pipelines, though this might not be the most efficient way. Pipelines are efficient for large-scale and continuous supply, for example to big industrial plants. However, hydrogen can make metals brittle. This is called hydrogen embrittlement. Because of this phenomena, pipelines require special materials and are costly. Hydrogen gas may also be compressed. Although in pipelines hydrogen is compressed too, but in containers the hydrogen gas can be compressed to very high pressures, usually 350 or 700 bars, and stored in cylinders or in large tube trailers that are transported by truck. This method is suitable for short to medium distances and for supplying refueling stations. High-pressure, compressed hydrogen storage is also used directly in vehicles that run on hydrogen as their energy source. The advantage is that the technology is available today and makes distribution flexible. The challenges are limited capacity per trip, and the fact that compressing the gas uses a lot of energy. In summary, pipelines are best for large volumes and continuous transport, while compressed hydrogen is more practical for smaller amounts and local distribution. Both methods are important parts of the hydrogen economy. Hydrogen can also be transported in liquid form. To achieve this, hydrogen is cooled down to -253 degrees Celsius and stored in insulated tanks. Transporting liquid hydrogen is more energy dense than gaseous hydrogen, which means more energy can be carried in the same volume. This method is used in aviation, space applications, and in some transport networks. The main advantage is higher energy density, which makes long-distance transportation possible. The main challenges are the very high energy cost needed for liquefaction, and boil-off losses over time as the liquid slowly evaporates. In summary, liquid hydrogen transport allows efficient energy storage and long-distance delivery, but it comes with technical and energy challenges. Hydrogen can also be transported indirectly, by storing it in so-called chemical carriers. These carriers are molecules that bound hydrogen in the structure. For example, ammonia is such. It has 3 hydrogen atoms bound to a nitrogen atom. Transforming hydrogen to a new compound can make transport and storage easier. Usually the high pressure is not needed, nor extreme cooling. But hydrogen carriers do have a downside too. It needs equipment, and hydrogen has to be releasable from the carrier, though not always. There are several important hydrogen carriers in use or under development. First, we look at ammonia. Ammonia, or NH3, is produced by combining hydrogen with nitrogen from the air. This substance becomes a liquid at -33 degrees Celsius, which makes it easier to handle compared to liquid hydrogen. Ammonia can be transported in tanks and shipped around the world. It can be used directly in some types of fuel cells or combustion engines even, or it can be cracked back into pure hydrogen at the place of use. The advantages of ammonia are easier transport and high energy density. The main challenges are its toxicity, and the need for special infrastructure to convert it back into hydrogen. Second, liquid organic hydrogen carriers, often called LOHCs. These are organic liquids, such as certain oils, that can absorb hydrogen in a chemical reaction, and later release it again when needed. This process is reversible. The benefit is that LOHCs are stable, non-explosive, and can be transported and stored at normal temperature and pressure. They can even use existing fuel transport systems, such as tank trucks and storage tanks. However, the process requires energy both to add hydrogen to the liquid, called hydrogenation, and to remove it again, called dehydrogenation. This extra energy demand increases the overall cost. Third, methanol and synthetic fuels. Hydrogen can be combined with carbon dioxide to make methanol or other synthetic hydrocarbons. These fuels are liquids that are easy to transport, store, and use in the same way as today's fuels. They can even be used in existing engines and distribution networks. The advantage is that no new large infrastructure is needed. The downside is that extra conversion steps are required to turn hydrogen into these fuels, which reduces efficiency and increases cost. In summary, hydrogen carriers like ammonia, LOHCs, and methanol provide alternatives to transporting hydrogen gas or liquid directly. They make long-distance transport and storage easier, but always add energy losses and costs compared to using hydrogen in its pure form. This is it for now. You will learn more about transportation and storage techniques in separate modules. Stay tuned.